So, I just need to make sure that everyone can. So, thank you everyone for attending.
Empowering the people who power our world. Since 1977, the Association of Energy Engineers has been leading the global energy community towards a clean and sustainable future.
Founded by Al Tooman, AEE emerged during a critical time when the world grappled with the oil crisis. Today, we're a global network of over 17,000 members and 32,000 certified professionals in over 125 countries, dedicated to implementing projects that improve energy efficiency, address climate change, and drive economic growth. AEE is a nonprofit organization dedicated to serving our members and other industry professionals by providing them with a framework where they can network, grow, and helping them stay abreast of the latest industry trends and empowering them to maintain a competitive edge through training and professional certifications. AEE developed the energy management profession. Our Certified Energy Manager certification is available in 10 languages and now has over 18,000 CEMs throughout the world. We also have certifications in energy auditing, building commissioning, sustainable development, renewable energy, carbon reduction, and a wide range of other specialized fields.
As we drive growth, innovation, and excellence across the industry, it's crucial that we empower all talented professionals to contribute. That's where CWEL, the Council on Women in Energy and Environmental Leadership, comes into play.
As a division of AEE, we are focused on supporting mentorship, networking, and scholarships for women.
The technical sessions were amazing.
The conference and expo is a great reflection of where we are at the industry. A lot of the exhibitors and content here is very current and very relevant, so it's a great way to come and get current with the industry.
What sets AEE apart is our commitment to driving change. We are a global family focused on putting people first and making the world better for current and future generations. The clean energy transition is happening now. So join us and be part of a community dedicated to this clean energy future.
Whether you're looking to advance your career, expand your network, or contribute to global climate goals, the Association of Energy Engineers is with you every step of the way. Together, we can shape the future of energy. Join us today.
The Association of Energy Engineers is a hub for energy professionals worldwide, a global organization dedicated to being at the forefront of energy innovation. So the AEA Greater Toronto Area Chapter supports energy professionals by promoting best practices in energy management, supporting professional certificates like CEM, CMVP, CEA, etc., and they were the ones that were mentioned in the video, creating a strong local network of energy and sustainable professionals, hosting events such as this, and advancing decarbonisation, energy efficiency, and ESG goals in Ontario and Canada. So we recently had an event on July 17th, which was in person at the St. Clair event in Toronto. That was in collaboration with CWEEL on the Council of Women in Energy and Environmental Leadership, which you heard from earlier. And if you want to know more about that, visit our LinkedIn for more. We'll have more in-person events coming up. Just keep posted on our website and our socials for events like that. Thank you for coming to this webinar. We also have another one on August 18th, which is Tuesday, and the registrations for that are live. So that's from the same time today as, or an hour later, 11 to 12 p.m. Eastern time. So please sign up to that on the website, and you may have received emails as well for that. To quickly talk through our sponsors for our chapter, we have platinum sponsors from Inspire, Carbon Cap, Edgecom Energy, Enbridge, Armstrong, and Ambient. Our gold sponsors are Honeywell and Grundfos, and our silver sponsors from Aladico, Kilmer, ENS, and Mitsubishi Electric. Now, to introduce our speaker today. This is the 10th Coffee and Conservation series that we have, and we'd like to hear and present to our members about condensing boilers performance in multi-residential buildings. And I've got an expert here from Carbon Cap, and they're going to talk through operational limitations and real-world efficiency outcomes. So just to introduce our speaker, Raphael, he's the Managing Director of Carbon Cap Inc., a Canadian clean tech company specializing in advanced heat recovery and building optimization technologies for multi-residential buildings and commercial buildings. His work focuses on practical decarbonization strategies that improve real-world heating system performance while reducing natural gas consumption, operational costs, and carbon emissions. Now, I hand it over to Raphael now. Just quickly, please stay towards the end in order to receive your 1-hour certificate on continual professional development from the AEEGTA. So with that, I'll hand it over to Raphael. Thank you very much.
Great. Thank you, Aidan, and I really appreciate this opportunity. Honestly, this venue is something that we didn't originally explore as a company as part of our mission statement, but as it evolved, we are really excited to be here. I guess I should start by sharing my screen. I'll set that up. Let's get that going, and let's just get the right screen here. Okay, this is the one we want. There we go. Okay. So I'm going to start with the talk today just about a short story, and it's actually goes back to my childhood. I was riding a bicycle across this field, and then I wound up in the back end of a commercial building, and I went up to the window like every curious kid, and I looked into the window, and I noticed that there was all these tables, and there was people sitting at them drawing and talking and discussing things. And it turns out later I discovered that it was actually an engineering firm that had architects and engineers drawing buildings and things like that. So I was always curious about what that was all about. And then someone, I guess about 20, 25, maybe 30 years later, came up with the idea of putting drawings digitally on a computer, and that changed the whole game. And so it's sort of a progression, this story of, when we started out with drafting boards and putting down our ideas on paper and then digitalizing it, and now we're having AI design a lot of these things. And so where am I going with this story? It's a great little story that certainly sparked my curiosity of ideas back in the day, but it just shows you the progression of where technology is taking us. And I think that's what the AEE I'm finding more is all about reigniting that spark. And I think as a result of the AEEGTA team and their curiosity about our technology solutions and ideas that are coming to the forefront, it gives them more of a hands-on look at things. And we can't always rely on AI to solve every problem for us. So I think that really is a big importance of the AE community, and the hands-on and the practical knowledge, and certainly the progression of information coming forward, not just from a computer, but from people that have experience. And so that's what leads me to write this white paper on the gap and the hidden efficiency we discovered in heating boilers. And so as a result of that, I came up with the idea of this white paper, and we focused it on multi-residential buildings. And it's not exclusively just to multi-residential buildings, but we certainly found that that was where there was a big gap. So let's get into our slide deck here today, and we'll discuss this a bit further. So the first slide here, I'll just pull this up, and here's an interesting chart. So I guess through Natural Resources Canada and other government organizations, various stakeholders, and different areas of the industry have told us that if you're a boiler manufacturer, going forward, we would like you to produce boilers that are the most efficient they can be, and they've set that threshold at about 95%. So if you've got an older building and your boiler dies, and you can't fix it anymore, you have to put in a high efficiency condensing boiler. And that's really what this presentation is about today. So let's look at that scenario. So if we are a boiler manufacturer and we tested our boiler and we've noticed that in the laboratory that we've met that threshold of 95%, we can market that boiler as a condensing boiler. And so in a laboratory, we can create many different things. Obviously, you have a controlled environment where you can test the boiler and make sure that it's operating at the threshold that you're looking for, and obviously a bunch of other things. And you can also adjust the return line temperatures to the boiler, and that's really an important thing. So when you look at a condensing boiler and this mandate to have a 95% efficient boiler, the only problem with that is that it requires a return line temperature that is below or at the dew point in order to provide condensing and to reach these efficiency goals that were set forward by the various organizations in these mandates. And so we studied that, and not just carbon cap, but also, various industry and organizations, from ASHRAE to studies that were done in the UK and the US and here locally in Canada, and we found there's about a 13% point gap. So most of the boilers are actually running at about 82% efficient in terms of their annualized efficiency. And so, well, why is that? And the big problem is that a lot of the boilers that, or rather a lot of the buildings that are out there are older legacy stock buildings, and we're trying to apply this new idea of putting high efficiency condensing boilers into these older buildings. And that's really what this study is about now. So there's the problem, the 13% point gap. How big a problem is this? Well, just in Ontario alone, we've got 1.8 million residents, and that represents approximately about 9,000 buildings. And we classify an apartment building about 5 units or greater. So we've got 9,100 of those buildings, and they, for the most part, are old buildings, probably built somewhere in the 70s, 80s, and maybe some even older than that. And how much of a percentage of emissions is being created as a result of these buildings and this building stock is actually quite high. It's around 55, 56%, and 47% of that is coming from heating alone. So almost half of the problem is the heating boilers. And so why are we not, addressing this, and what is the problem? Well, we've set a mandate to put in high efficiency boilers that's going to correct this problem. However, statistically, it doesn't seem like we're going in that direction. In fact, we'll talk about that a little bit later in the slides, but it looks like we're actually increasing by 1.7% in terms of the carbon emissions in Ontario, versus the decline of about 11% needed to hit our 2030 targets. So we'll just go to the next slide. From a technical perspective regarding the condensing and the operation of the boilers, like I said, when you're in a lab and you've got a mock boiler facility and you're able to control the return line temperatures, you can see in the middle of the screen, the dotted line is the condensing threshold, which is 130 degrees. It's not a static point. It could be a little bit higher, a little bit lower. You will get some condensing, but that's really where these efficiency numbers are coming from. And if you can see, in order to hit that 97.5 on the left side of this inverse hockey stick, you'll see that the return line temperature actually needs to be about 80 degrees Fahrenheit or less. And that's in order to hit that target. But there's challenges with that in older building stock, and that's really what we're talking about here today. So we've coined this as the 130-degree cliff, but it's more of, you know, the dew point, and its variance somewhere in the neighborhood of probably 120 to, you know, 138, 140. So boilers are able to condense depending on the various situations, but just not to the point where they're going to be at 97%, and they're going to hold that number as an annual efficiency number. So let's look a little bit deeper into the return line temperature and what's happening in the building. So we have identical building here. On the left side, we've got a boiler signified by the white area and a heat exchanger in the middle, which is its internal working heat exchanger. It uses the heat exchanger inside to transfer the heat created by the fire tube boiler to, you know, obviously the water that it's attempting to heat up. And so if we look at the return line temperature potential on the left side of the screen, we're noticing that there's a deep red line coming down signifying flue gas hitting the heat exchanger, and the return line is still quite warm. So we're not too sure at that point how much condensing is happening, and we're looking at the left side of our screen, and we're assuming that if you've got a return line temperature of 150 degrees, that becomes problematic for any condensing. And you truly need a return line temperature, like we mentioned, below 130 degrees, which would be the, you know, the dew point threshold for condensing to start taking place. And if you look on the right side of the screen, we've got a heat exchanger with hot flue gas coming in and a blue line on the return. So obviously there's more condensing potential on the right side of this screen because you've got a lower incoming water temperature on your return loop in your building. And we notice that that just is not something that's happening, particularly in these legacy buildings. And we'll get into that a bit further on the next slide and discuss that. Why is that not happening, and why is the return line temperatures not lower? And I mean, we're engineers. Why don't we just go into the boiler room and have our stationary engineer or our mechanical service guy turn down the temperature, and then we'll get all the condensing we want. Part of the problem is we have occupants in the building, and they're looking for some heat to stay warm. And in order to do that, we've designed these buildings that have emitters in them, so radiators. And these radiators have a designed output, of so many BTUs. The average apartment may have 2,500 to 3,000 BTU radiator. And in order to reach those BTUs, as per the engineering design for the building, the problem is that we have to send it a specific temperature. So the supply to that radiator needs to be about 170 degrees. And as a result of the conditions that boilers require, you can't have too large a delta T coming back to that heat exchanger. And if you do, it's going to create havoc on that heat exchanger. It's not going to like you. You can push it to 25, 30 maximum degrees delta T, but the designed return temperature is usually 20 degrees. So if we've got a legacy building and we've got an input temperature of 170 degrees, it's going to be coming back at 150. And so that becomes a problem. There's not going to be any condensing. And that's quite frankly part of the challenge of why we can't just simply turn down the temperature. Now, what would happen if we did turn down the temperature? One thing that would happen would be we're not going to get the number of BTUs out of the radiator that's required. And so, in fact, if we turned it down approximately, 30%, 35%, we would see a 64% output. And therefore, the apartment, or rather the suite, is going to get colder, and the occupant obviously is not going to be as comfortable. So this is the problem with installing, basically a condensing boiler that has, obviously the ability to condense, but if we're not running our water temperatures at the conducive condensing, levels, there's no hope of that boiler condensing. And again, this is something that works perfectly in a brand new building, because you can design your emitters and your radiators to be low temperature. In fact, some of the modern buildings are using radiators that need as little as 140 degrees supply temperature. So if you're putting 140 as your supply, your return could be 120, and you're going to get a fair amount of condensing. Now, keep in mind, our graph said you still need 80 degrees to get your full condensing. So that's going to be problematic. And something else that isn't mentioned on this slide is the domestic water requirement. So if you've got a set point of 135 degrees Fahrenheit, just above, obviously, the Legionnaire's requirement, some buildings may run a little bit hotter, about 140 on your domestic water. Again, you can get some condensing from that because your return is 20 degrees lengths. But you need to decouple your heating loop from your domestic water loop. And the white paper we wrote talks about that scenario. We won't get too deep into that today. But you can see the challenge of the water temperature and how important it is to understand the supply and the return line temperatures. I'm just going to check the next slide here. So here we go. So how can we fix this problem? We've decided that there's probably 4 different pathways to fix this problem. And when I say, problem, meaning the building efficiency, not just the boiler and its condensing. We've discussed the problem, and we've discussed why it's happening, so we could obviously draw a conclusion in that regard. But there are other things we can do in a building, as we know. That's why the energy engineering community wakes up every day with a smile and tackles these problems. So our interpretation of one solution is obviously controls and tuning. So if the boiler is not firing correctly, maybe it's an older building that doesn't have an outdoor reset. It's a wonderful warm day in the spring or shoulder season, and your building is running a high temperature loop for no reason at all. So obviously having an outdoor reset can have some very reasonable returns in terms of efficiency. And we've measured those and studied various results ranging from 6 to 10%. And again, how you have your boiler tuned up, is the heat exchanger been cleaned on it? Is the air filters good? Do you have any venting configuration challenges? And how can we get that? Those are just really simple mechanical things. And in terms of cost, economically, fairly reasonable, and there's a lot of service providers that can do that. The second, tier 2, again, I mentioned decoupling the hot water. That's definitely a way that you can solve some of this condensing problem. A lot of buildings may be using older style pumps. As Aidan mentioned, the AE is going to be doing an Armstrong presentation, and I'm sure they'll talk about how VFDs and obviously having the right pumping and domestic optimization in terms of your hot water supply is important. And these are, I would say, more moderate challenges for a building, not just in terms of the mechanical fix for it, but the engineering is pretty straightforward, and the cost, would be reasonable, something to certainly look at guessing anywhere, could be on the low side from 10% as much as even 15% or more for optimizing these things. So each project would have its own result. The third fix and the third tier of our solution expectation would be obviously to go back to our original slides and figure out, well, how can we get that return line temperature down? And one of the ways to get that return line temperature down in the building would be obviously to change out the emitters. So they're low temperature emitters. Like I mentioned, they probably only require 140 degrees. And that 140 degrees could be satisfied by a heat pump system, most likely air source. Again, there's always, that worry that we're going to have that super cold day. The past few winters, there has been some pretty cold days and spells, and sometimes that requires a heating boiler supplementation for that. So heat pumps are definitely a solution in that retrofit scenario. And obviously you would have to redesign your hydronic loop. But just changing out the low temperature emitters is only one aspect of that. You would actually have some concerns regarding the piping to all those emitters themselves. And if you just change out the emitters and put in your condensing boilers, technically you've satisfied the equation. You've fixed the return line temperature, you've got your BTU requirement, your tenant is happy, they're comfortable, occupant rather, and we're all set. The only problem is you've got some old pipes in that building, and if the fittings aren't tied to tight enough or correctly, or there's some blockages because the building has been not really keeping an eye on its water treatment on its closed loop, then that can create some definite problems. Things we like to call them sprinkler heads in a building. So that becomes a problem in an older building. So the only way to really fix that would be to replace the actual conduits that lead from the boiler loops to the actual emitters themselves. And that's obviously a really deep retrofit that a lot of building operators are not prepared to pay for and have trouble substantiating. So we have a fourth solution, and one of them may be looking at any type of waste heat recovery. And so there's flue gas heat recovery as an option. And what does that actually do? So if we've got a boiler that's only, it's receiving 170 degree, output temperature with a return of 150, the odds are its flue gas temperature is going to be above 250 degrees, maybe even 350 that we've seen in the field. And so that's wasted thermal energy. If we could capture that wasted thermal energy, we could put that back into the building, and we could do a couple things with it. We could actually preheat the incoming cold water to the building, and then we could also take that line and preheat the boiler's return. And so what does this do in terms of our overall efficiency? So if the boiler's running at 82, 83% efficient, we've got a 17% loss. And so that 17% loss, where is that going? We've noticed that it looks like about 15% of that is going up the stack. And then another percentage is being lost through the actual venting materials and the boiler wall itself. And so that makes up your 17 to 18% of efficiency difference. So if we could put that back into the building, then that could possibly help us. And we've analyzed one system, and we've noticed that it's providing 11% efficiency back. So even though we have this high temp emitter and this, either a traditional boiler or condensing boiler, it may not be condensing, and it may be wasting some high temperature flue gas. And so as a result of the flue gas heat recovery system, we've studied that and realized that it can provide 11% benefit. And so that is basically your four opportunities when it comes to retrofit options for existing buildings. I mean, obviously you've got building envelopes that you can correct with insulated facades, and you can start going down all types of different roads in terms of other costly improvements. But it's really, how do we come up with some solutions that are clear pathways? And that's why I believe these four pathways are certainly an organized way to look at what we can do to fix the problem. I'll just the next slide here. So let's look a bit deeper at this waste heat recovery and what actually happens. So I mentioned we've got 11% coming back in terms of efficiency that we've studied. But this particular arrangement is basically reviews what I just said. So we've got that wasted 250 to 350 degrees flue gas that's leaving the building. And it's also leaving with emissions in it, about a 7% CO content. And so it's got other greenhouse gas problems in it as well. So it's adding to that emission number that we spoke of, that's increasing by 1.7% in Ontario. So this particular system here shows the incoming heat to this recovery plenum, and it's coming in between 250 and 350 degrees. And what happens is we, with this particular technology, we're able to take that flue gas temperature and take that 350 degrees and turn it into usable thermal energy that preheats the boiler return. So when we've got a boiler return that's high at, say, 150, we can actually bump it back to about 160 before it hits the boiler again. And then it only has to go back up to 170. So instead of having a 20-degree delta T, we're sending that boiler back 10 degrees of its return line. So that's the improvement that this system can do. Now, after that flue gas temperature has dropped from 350, 250 degrees, it'll drop down to the return line temperature of the boiler, which we've mentioned 150, but it really depends on what the boiler's doing, what firing rate it's at, and the average return temperature can usually in this recovery system be around 130 degrees. Now, what's the magic about that middle number with the arrow? It's 130 degrees represents the dew point, and as we talked about earlier, the dew point is really what we need to get condensing. And so now that we've done the waste heat recovery, what can we do with that 130 degrees? Well, the average waste heat recovery system would just continue to simply exhaust it. But we've got another solution. We've actually decided to take that 130 degrees and use it to preheat the incoming cold water. So if we've got cold water coming into the building approximately at 50 degrees Fahrenheit, we're able to expose that 50-degree water now to the 130-degree temperature flue gas. And so what happens is the first part of this recovery plenum has captured the sensible energy, and the second half now is capturing the latent energy. And the latent energy is really where you get your high value in terms of your heat recovery. So now we've got 130 degrees that's going to hit 100 and, or rather 130 degrees that's going to hit 50 degrees water, and it's going to bump that not of a delta T of 10, but sometimes as much as 50 degrees. So that 50-degree water coming into your building will now be 100 degrees before it gets to its tanks to be blended, obviously, with the boiler heating loop, and it'll bring it up the rest of the way. So now we've actually gone from 350-degree flue gas to a final exhaust temperature that usually matches the temperature of the incoming water. And if that happens, that means that we've captured all of the available thermal energy from that flue gas. So remember how we talked about the efficiency problem and how we can fix this legacy building with these existing boilers or even a condensing boiler that's not condensing. is we can use this flue gas heat recovery system. And this is a very modest, I would say, modest to moderate, depending on the venting arrangement in terms of the economics of it. And in terms of the building disruption, it's very simple. It's all being done in the boiler room itself. How do we know this works, and why am I able to speak on this heat recovery plenum that we've talked about? Well, Carbon Cap has actually been involved with the development and study of this system and this heat recovery solution. Remember, we had 4 solutions. This is just one of them. And that started out several moons ago by simply coming up with the concept and doing some initial testing, and not just at a local college, but level. As you can see, a couple students, and both of them engineers now. One of them recently became a certified engineer, and we're quite proud of that. And so these gentlemen are testing really what the circulation requirements would be on this system. So in a laboratory system, we eventually migrated the initial idea to a mock boiler facility. And then we were fortunate enough to receive some funding from the federal government and create this wonderful mock boiler room that I spoke of earlier. And it's not just our company that has these mock test facilities. Obviously, large boiler manufacturers have their own mock facilities where they test items and publish reports, and obviously have oversight not just from the federal government and various organizations, but obviously, people like ASHRAE, and they have other, safeguards to make sure that their boilers and their testing results are actually certified and done the right way. So after that, in about 2023, February 5th was the day we commissioned the system. We were able to put it into this building just not too far from Lawrence and Bathurst in Toronto. And this is the heat recovery system now migrating from a mock boiler facility to a live building. And this live building has been running with this heat recovery system flawlessly since, I guess, 2023. Then we've decided to take, a little bit of the metering more seriously. So instead of using, heating degree days and gas bills and, estimated temperatures, we've installed some certified metering, and we actually have 771 days of EN 1434 compliant, Measurement Canada compliant, calibrated meters in the both returns. Remember, we talked about having the boiler heating loop return and also the domestic water. So we have meters on each one of those legs, and it's showing, again, 11% is the increase in efficiency when you take the amount of BTUs that these meters have recorded and continue to record in terms of their thermal metering. So that's how we know it works. Getting back to the first slide, we talked about carbon emissions and where they're all coming from, and what do these numbers mean of these 9,000 buildings. So this is the problem. We've got various organizations that talk about the climate goals that we have, but when you look at the actual results of some of the organizations that are publishing those, we see a 1.7% increase. So building emissions are rising. And remember, we said 47% is the heating boilers alone. And so isn't it interesting that the required trajectory in order to meet our carbon emission goals needs to be about 11% less? So if we could get a heat recovery system into all 9,000 buildings, we would meet the climate goals. The good news is there's more than just heat recovery. There were 4 pathways, and certainly the collective effort will hopefully help us reduce our carbon emissions to where they need to be. what's an important factor in this presentation? It's about getting the information out there to the AEE community and certainly to other stakeholders like the building owners, the government, investors, engineers we've mentioned, and certainly the utility companies are heavily involved in helping not just the building operators, but collaborating with innovators and manufacturers like us to help reach these goals. So we really need to think about what needs to happen in terms of this collaboration and how can we make this happen and move it forward. And I think it's venues like this today that help us expose that and bring really answers that are much needed to meet our climate goals. And also comfort levels in the building will get better. The building operators will be happier. They'll have lower operating costs, and in the meantime, we're meeting our climate goals. So that's the presentation today. I've got a full 60-page white paper that's available for anybody that's interested in looking at it. We'll certainly just email us and we'll get you a copy of it. We're going to be posting this on our website eventually. Right now, the white paper is being reviewed by several key stakeholders, and so far the reviews are quite good. I also have a short version of it, by the way, a 2-page document that basically says a lot of things we talked about here today. So happy to answer any questions involving this, and if anybody would have those questions, I'll pass it back to Aidan, and we'll go from there.
Thank you very much, Raphael. So let's get into some of the questions. First of all, I'm unsure if this... Would it be possible to receive the mentioned white paper that you have been talking about?
Yes, 100%. It's ready to go. It's in its final form. So I would say just email us, and we're happy to pass it along to us. And eventually, it's going to be on our website as well. If you just go to carboncapinc.com, send us an email. I'll make sure you get a copy of it, and I'll send both versions of it, the light version and the heavy version. Some of it's some deep reading, but it's actually some really amazing people we met during Toronto Climate Week. A couple engineers, they took that paper to the ASHRAE conference, spread it around a little bit, and the reviews have been quite positive. So we're excited about that.
It's very good to hear. What boiler capacities can the flue gas heat recovery support?
Yeah, so we can basically go up to, the biggest building that Toronto has. So if you've got a 500-600 unit building, you're probably running anywhere from 6 to 10 boilers. So it has a limit of about 10 million BTUs, and it actually doesn't recover 10 million BTUs, but the capacity would be about 10 million BTUs in boiler capacity. Now, remember, those 10 million BTUs, some of those BTUs are being used by heating the water. So it's not that 10 million BTUs are left over, but the system could handle usually, up to 10 million BTUs.
And what if you don't have a DHW boiler in the building? Where else can the latent heat be used?
Right. So in most buildings, that's a great question. Most heating loop configurations will have basically a header, and that header will be at that 170 degrees, and then you have a line off that header that heats your domestic heat exchanger. And so a lot of times we'll look at the temperature gauges on those return line temperatures, or rather the output to that domestic water, and it's actually usually running way too high. So we actually put a 3-way valve in there that throttles it, and we're able to recover some of that return line heat and improve the efficiency of it. So not only just the boiler return, but we are also taking some of that header loop that would be going to the domestic water. And then the cold water coming into every building, it doesn't matter what building it is, you're going to have cold water coming in at one point. We steal that cold water before it gets to the heating tanks or to the heating loop, and we put a 1 foot bypass in, and that allows us to do it, to preheat it.
Perfect. So those questions were from Anna Shen. If you have any follow-up questions, please feel free to ask. And just so, Benham, you were asking about the white paper. I've put Raphael's email in the chat if you want to follow up with that as well. We have a question from Asif Mohammed, who says, how much better is the flue gas recovery performance compared to using the return water for preheating incoming cold water?
Right. So it's actually quite a bit. So we really will notice that probably, I think we actually have the statistic numbers. It's about 40% on the boiler heating return, and then 60% on the domestic water. So you're getting the big bang. It might even be closer to 65%, 35 in terms of the, but it really depends on the building. So yeah, good question. For example, an office tower, you may not have a lot of domestic water. Will you get 11% benefit? Probably not, because you don't have any incoming cold water. So that's a great question. So you can see, obviously, the sweet spot for the system would be having domestic cold water coming in.
Thank you again. So from Delani Faisal, what would be the efficiency improvement if a flue gas waste heat recovery is used with a non-condensing boiler as opposed to a condensing boiler?
Yeah, it really just, it really depends on the building itself. So if the emitters in the building are requiring, like I said, the 170-degree loop, they're never going to respond to condensing boilers. So in fact, we go into buildings all the time, and we've seen that a lot of the boilers are just not condensing. And that's what these studies are all about. So I think it really boils down to, can the building operate efficiently with a lower return line temperature? And as soon as you install those condensing boilers, you'll find out, because your occupants are going to say it's too cold in here, or you'll notice your temperatures. If you have any way of discovering it in the suites, you'll notice that your temperature is not warm enough. But the system will obviously provide a benefit under both scenarios. But it's really about, what is your return line temperature? So yeah, ultimately the building operators are going to need to only install high efficiency boilers. But now it becomes a balancing act and more of an engineering thing. You don't want your temperature going up and down too quickly, because what we've noticed is a lot of the boiler manufacturers are having problems with that, because the heat exchangers are not as large as the old school ones. They're smaller, and the metallurgy on them, by heating them, cooling fast, actually creates a problem for these heat exchangers and these boilers. So it's really building specific, and it's a complicated answer, but yeah.
Thank you again. We have a question from Mark Armstrong. Are you using a separate flue, or do you tie it into the existing? I'm assuming this is a positive pressure flue.
Good question. Yeah, a lot of building owners and a lot of associates that have come to our system, say, oh, couldn't you save money and just use the same flue? And that actually came up recently in New York City. One of our clients down there has a substantial portfolio, and they were saying, we're going to change out some of the boilers. We're going to put this brand new big stack, and you can just use that stack. And I'm like, no, I can't. And why we don't do that is, first of all, is we're fully condensing all the available flue gas energy. So if you've got existing vent material that is not condensing available, creating a bypass and putting condensing temperatures into it is a problem. And you're also cavitating the rest of the boilers down the line, because you can't start putting a draft inducer on that line and then drawing flue gas through a common header that could be pulling air off some of the other boilers. So it's just so much easier. We just have a separate flue, and we're venting them in the right way, so all the condensate is flowing out of them. An incredible amount of condensate is produced. Just to give you an idea, in that photograph of that building where that heat recovery system was tested, we received about 20,000 gallons of condensate a year from that building. 20,000 gallons. So the average condensate filter on a condensing boiler is about this big, and it's capable of doing maybe 1,000 gallons a year. we notice that there's usually less than 200 or 300 gallons of condensate from the average condensing boiler in these legacy buildings because there just is no condensing. So we need a separate flue. The best animal for this is a rooftop boiler room. And that way it's easier to get an extra flue installed in it. And that's really where the economics come in and the building specific. So yes, we do need a separate, and it also provides some redundancy, okay? So you've got existing boilers, they've got their own flue, and then you've got your heat recovery flue on this side. If anything happens to the heat recovery system, the boilers continue venting by themselves. So you're not blocking the flue, and that's why that particular system has all 29 claims approved in 8 different jurisdictions because of that redundancy factor. In fact, it has about 7 redundancies.
Perfect. Thank you. That's a very good, interesting answer. So could you please comment on the cost of non-condensing boiler plus flue gas heat recovery system versus condensing boiler? That's from Daoud Ilyas.
Right. Perfect. Obviously it boils down to economics. I think condensing boilers are, it's the boilers themselves are going to cost you 30-40% more. And then obviously you've got all your venting arrangements that are different, and you got new mechanical costs, engineering. But you can't just change out an existing fire tube, say atmospheric or mid-efficiency boiler for a condensing boiler without having engineering, planning. Are you decoupling the domestic water? So there's more considerations on that. So the short answer is 30-40% more. And then obviously you've got approximately $100,000 cost for the heat recovery system installed. Those are Canadian dollars. And so, when you put the two together, if you used an older boiler and you did that system, and here's the benefit. The older boiler may have 10-15 years left in its life. And if you're improving the efficiency by 11%, you've just added 2 or 3 years to the boiler's life as well, because it's on 11% less. So when you do the full life cycle economics of having an existing building with existing boilers, not disturbing anybody, putting a retrofit on, and having 11% improvement, and extending the life of the boilers. And that's really what this system is about. And that's really what those 4 pathways are about. It's about transitioning everybody to get them to this net zero world. And we have other solutions that solve that problem, by the way, at the end of that life. And if you want to spend the money now, we can actually solve those before. But in the meantime, if you've got a building operator that just wants to get his utility consumption down, meet his carbon emission goals, the waste heat recovery system is the way to go in terms of my economics that we've come up with. And certainly the white paper talks about those economics as well.
Perfect. So further reading for anyone interested.
Yeah.
We've got about a minute or so for any more questions. And if anyone has, feel free to ask just now, or also direct those through the email to Raphael, or you can send it to us as well at AEEGTA. So I will just share my screen. Give me 2 seconds. So I'll pause here for a little moment while you can see the QR screen or QR code on your screen. If you scan that, that'll take you to a membership as part of the AEEGTA. While we're here, I just want to say thank you to Raphael for that lovely presentation and interesting questions as well from the chat. Thank you all for taking the time to come along. The slides themselves will be sent out after the fact, as well as there'll be a video. The recording of this will also go offline on our YouTube as well. So there should be an email that you'll receive after the fact. You can get all that information. So become a member today. Professional memberships $60 and students is $20. My slides are not responding. Okay, there we go. So yeah, thank you for making the time. Thank you for coming along. If you have any other questions, again, direct them to Raphael or us. And if you'd like to contact us, you can email us at the president at aeegta.org, or go on our website. You can see all the events that we do, and we have a webinar coming up as well. Yeah, keep posted. Thank you all for attending, And if you have any other questions, please put them in the chat and we can spend an extra 2 minutes just now, or you can go about your day, and thank you for spending time with us.
We've got one question there. It talks about the how low can we go in terms of the, or how small can we go? I think it really depends on the building. I mean, I would say, you know, you want a building of at least 75 units that consumes about 150,000 meters of gas. I don't know that you'd want to go any smaller than that. And part of the problem is the cost of the natural gas. So if you've only got a $60,000-$70,000 a year natural gas cost, and you've got a $100,000 equipment install, you know, your payback is going to be extended. So the benchmark building for a heat recovery system to be economically viable in Ontario right now, with no carbon emission penalties, is approximately about 250-300,000 meters of gas. So you've got to have a pretty substantial building, about a 200-unit building. Again, it's really all about the building operator's goals and how they interpret, you know, the effectiveness of the economics of it. It could be just the cost of gas and the savings. It could be the asset appreciation value. It could be hitting your carbon targets, which is important for your organization. Or it could be just extending the life of your equipment and you're placing a value on that. So again, we like to see about a 250-300,000 meter gas consumption in order to make the project effective. And it says, have any existing condensing boiler manufacturers work with that? One of our strategic partners is Mestec, which is RBI Boilers, incredible organization. We've also spoke to a few others, but certainly RBI has been one of the most generous proponents of this. And why would a boiler manufacturer work with a company that takes their flue gas and does things with it? Well, because when the boilers come to their end of the life, we've got a great relationship, and we're obviously going to tell them what boilers that we think are really good. And so to answer your question, yes, we do work with boiler manufacturers. And that's a very important point in New York City as we're working towards our DOB certification, which we're very close to getting statewide approval in New York State on, and they wanted to know about our relationships with boiler manufacturers. So that answers that last question, I think.
Thank you very much for that, and thank you again, Anna and Ershad, for those questions. So we'll leave it there. Thank you all for attending, and have a good rest of your day. Thanks again, Raphael.
Perfect. Thank you.